In our last example, we took a Taylor polynomial that we had already picked, and we figured out how small our error was guaranteed to be based on Taylor's theorem. That was kind of contrived because it assumes that we've already picked what kind of Taylor polynomial we want to use, and we don't actually care how accurate it is other than to just report on it at the end. What we would typically be more interested in is picking out a Taylor polynomial based on a specified level of accuracy. So for example, if I was trying to make a calculator calculate, in this example, the natural log of 1.2 using a Taylor polynomial, and I want to guarantee that I am within 0.001 of the correct answer, I might be interested to know how many terms of that Taylor polynomial do I need? Or another way you could say that, what degree Taylor polynomial is necessary to make sure I'm within 0.001 of the answer? Okay, so let's try to work that out here. So the first thing I want to do is make sure I know what my Taylor polynomial is going to be. So since I don't know what degree I'm going to use, or in other words, what's my n I'm going to go up to, I'm just going to find the first few guys and see if I can find a pattern here. So the function is natural log of x. The derivative of that is 1 over x. The derivative of that is negative 1 over x squared. The next derivative is 2 over x cubed. Okay, the one after that, I'm just doing enough to kind of get the pattern here. Negative 6 over x to the fourth. So let's see if we can start to work out the pattern here. I want to figure out an expression for the nth derivative of this guy. So let's look at the top and see what the pattern is there. 1, 1, 2, 6. At this point, I'm hoping we can start to recognize that pattern. 1, 1, 2, 6. The next guy would be 24. The next guy would be 120. These are just the factorials, right? That's 0 factorial, 1 factorial, 2 factorial, 3 factorial. So I do want you to start noticing this pattern here. If you see that show up, notice that that's factorials. If you want to convince yourself more, try out the next few terms and confirm that that pattern still happens. So I've got a factorial, but if I'm looking here, this is n equals 1, this is n equals 2, so it's not n factorial, it's actually n minus 1 factorial. Okay, it also flip-flops between positive and negative. So when n is equal to 1, I've got a positive. When n is equal to 2, I've got a negative. So I'll write that as negative 1 to the n plus 1. And then finally, on my denominator, I've just got x to the n. So my nth derivative is going to be n minus 1 factorial times negative 1 to the n plus 1, all divided by x to the n. Okay, so that was just kind of some pattern recognition there, seeing if I could match what's going on to a general definition. All right. So I've got my nth derivative. Let's see how I can use that with Taylor's theorem. So I've got Taylor's theorem up there as a reminder for us. So if I was going to use a degree n Taylor polynomial, okay, let's write what I know about that. All right, so I'm going to plug things in as I know them. So I should be plugging in 1.2, and I'm centered around 1, so I know those guys. So that's going to be 1.2 minus 1 to the n plus 1. Over n plus 1 factorial times the max of the absolute value of the n plus first derivative evaluated at z. Okay, now I'm not going to worry too much about z yet. First, I'm just going to make sure I understand what the n plus first derivative is. I figured out the nth derivative, so if I want the n plus first derivative, I'm just going to take this formula here and plug in n plus 1. So n plus 1 minus 1, that's n factorial, times negative 1 to the n plus 2, all divided by x to the n plus 1. Okay, but remember, I'm actually supposed to be plugging in z, so instead of writing an x there, I'm just going to write a z. All right, now I can do a little bit to simplify this at this point. So let's see, I've got 0.2 to the n plus 1 over n plus 1 factorial, and now here, since I'm just trying to find the maximum according to what happens with z, I can go ahead and bring out this n factorial. Okay. Also, if I take the absolute value of negative 1 raised to any power, that term's just going to go away. So I'm really just looking at the maximum of 1 over z to the n plus 1. Now I can pay closer attention to what's going on with z. Z is supposed to be some number between x and c. So that's between 1 and 1.2. So I'm thinking about all the numbers between those two slots on the number line, and thinking about which of those numbers in that range would make 1 over z to the n plus 1 as big as possible. Okay, so because it's a fraction, and I'm trying to make that fraction as big as possible, I want to make the denominator as small as possible, which is going to happen if I plug in 1 for z. Okay, if I plugged in 1.2, that would be a bigger denominator. Don't want that. I want a smaller denominator. Okay, so it turns out that whole term just turns into 1 in this case. That would be if I let z equal 1. Okay, so that is the error I get for the nth term. But now let's think about what the problem's asking us to do. I can do one more step here. N factorial over n plus 1 factorial. We've actually practiced this before in some homework. This is all the numbers 1 through n on top. And on the bottom, I've got all the numbers 1 through n plus 1. So everything cancels out except the 1 over n plus 1. Alright, so this is about as cleaned up as I can get it. 0.2 to the n plus 1 over n plus 1. Okay, now I want to make sure that this error is less than or equal to 0.001. That's what the problem requests. Okay, so I just want to find the first value of n that makes this expression smaller than 0.001. So I could either go through manually and plug in some values, or I can have the calculator kind of do this for me. So I want to show you how to have the calculator do this for you. I'm going to go to y equals, and I'm going to plug in this function right here. So let's see, this is 0.2 to the x plus 1 divided by x plus 1. Notice I'm using x because it's inconvenient to use n. So there's my function, and instead of looking at the graph, I'm going to go look at the table. Now I already kind of have the table set up the way I like. Just to show you what I've done, table set, I just want to make sure independent is set to ask. Okay, all that means is I get to pick the x values I'm going to plug in here. Okay, so let's go back to that table. If I plug in n equals 1, darn, my error could be as big as 0.02. That's not good enough. If I try n equals 2, nope, still bigger than 0.001. What about n equals 3? Let's see, that would be I'll go highlight this. That would be 0.0004. Yeah, that would actually be good enough. Okay, so the first value of n that makes this inequality true is n equals 3. So what that tells me is that, let's see, find the smallest value of n guaranteed to estimate it accurately. Apparently that smallest value of n is 3, because when I plug in 3 into Taylor's theorem here, I'm guaranteed by Taylor's theorem that my error is going to be not just smaller than 0.001, but actually smaller than 0.0004, according to the calculator. Okay, so even with just a degree 3 Taylor polynomial, that is extremely accurate. If I needed better accuracy, I could just make n even bigger, right? That might be a different question I could ask. Maybe how many terms would it take to get it to an error less than 0.000001? I could figure out what n would be for that as well.